Okay, Assalamualaikum warahmatullahi taala wabarakatuh. I am Muhammad Azamudin bin Mu'abani with number 1 street CE230047. Today, I am from group 3 will presenting about introduction. The RLC circuit consists of resistor R, inductor and capacitor linked in a variety of configuration. It is an important and commonly used component in the field of electronic and electrical engineering. The resistor is a passive element that loses energy in the form of heat and opposes the flow of current, as indicated by its resistance in ohms. The inductor is a passive element that stores energy in its magnetic field when current flows through it, resisting change in current, and it is defined by its inductance in henries. The capacitor is a passive element that stores energy in its electric field when voltage is applied across it, resulting in voltage shift, and this is defined by its capacitance in farad. State analysis is the approach for analyzing the behavior of an electrical circuit after it has been stabilized during steady state. Voltage and current in the circuit will remain constant throughout time. This study is particularly useful for determining the response of sinusoidal signal or DC input in a RC circuit. In a stable state analysis, phasor represents sinusoidal signal or time-varying input with complex number that measure the magnitude and phase of the signal. Using phasor, a time domain analysis becomes a simplified algebra problem in the frequency domain. To solve a collection of equations simultaneously, techniques such as Kirchhoff's law, Ohm's law, and impedance theory are used in the analysis. Impedance describes the complex ratio of voltage to current for components like resistor, inductor, and capacitor. Power, resonance, and responsiveness to different frequencies can all be calculated by calculating phasor, voltage and current at different locations in the circuit and translating them back to real-time domain representation. Steady state analysis is critical for understanding the behavior of RLC circuit under AC alternative current and circumstance, and it's widely used in the design and study of filter, amplifier, and other electronic systems. It allows us to predict and optimize circuit performance in steady state condition, assuring adequate functionality and obtaining desired features.
Assalamualaikum. My name is Muhammad Zaid Michael bin Zainuri. So today I'm going to show you about simulation of question 1. So from the question, we assume a current source Is of 8 ampere is applied to the circuit. So we must find the initial current and the initial capacity VC above 0. So we must use omega in the range 100 until 1000 hertz. So each group must use different omega value in the design. So from what I get from the circuit, so I use a multi-C. Firstly, I will do a critical damped. Critical damped is, I assume, 50 ohm to 250 millihenry and 25 microfarad. So this is circuit. After I build the circuit, so this is, I use step current to get a weight. So I will run the circuit. So this is the critically damped. I get. So this is 8 ampere. So voltage is 0. So I as current 8 ampere. We showed it 8 ampere. So after that, we go to overdamp circuit. Overdamp circuit, we use 25 ohm and 250 millihenry. Still same. This value still same. This our current notation and voltage notation. So we run this circuit over them. This is over them. So I must edit this name to over them line. Okay, this is over them circuit. We must still use 8 ampere. So this is 8 ampere. So okay, next is under them circuit. Under them we use 75 ohm and 250 millihenry. Still same value, and also 8 ampere current. So we run this circuit. This is of under them graph, under the transient graph. So this is under them circuit. Okay, that's all from first half. Okay, next we must find the VT. We going back to report. So this is IoT. What I get, okay, I make overlay the graph. So there are 3 response transient. So next is we found a graph of VCT for voltage. So let's go. So this is for critically damped. We just put the voltage here. So we run again voltage notation. Which is the critically damped for voltage. So critically damped for voltage. Okay, turn off the current legend to see the graph of voltage. So next we must do a same step to over them and under them. Next we run. Okay, this is our over them transient, over them graph. Over them for over them graph for voltage. Okay, next we must use same steps. Okay, and we run it. Okay, this is our under them graph. This is under them graph. Okay. And from the reports, I will overlay all the three response for voltage, and this is what we get. Okay. And that's all from me. Thank you.
Madania Camioso, CE230018. Today I want to present about question 2 with a calculation and video simulation. First of all, this is our questions, and we go to the answers solutions. This is our solution for this. First of all, we must to change the 10 since omega t amperes, like we get it is 10 since omega t plus 90 degrees, so we got the 10J, and we change the voltage total to 20 degree, and we got the 20 volts. So we must to change the capacitor and inductance to, we know that the negative J per and omega c, and the inductance is J omega L. So we go to the next is a mesh. We use a mesh solutions, and next we use a Kramer rules to solving the questions. This is our Kramer rules. And next, this is my final answer for all of the questions. We got a 10 cos of 200 omega t plus 84.28 degree. So IB is 0.02 cos 200 omega t minus 91.72 degree, and the IC is 0.015 cos 200 omega t plus 89.47 degree. And the lastly is voltage for this is 0.01 cos 200 omega t minus 1.8 degree. So we go to the summations. This is our summations. This we go to the graph for IA. This is our graph for IA, and the next is for IB. This is for the IB. Next we go to the IC. This is our graph for IC, and the lastly is the graph for the voltage total. That's for all for me. Thank you.
Okay, hi again. As a conclusion, finally, the RLC circuit is made up of a resistor, a capacitor, and an inductor connected in series or parallel across a voltage supply. The damping of a circuit is calculated using alpha and omega. Then we develop three different types of second-order circuit and successfully estimate the inductor current and capacitor voltage. We then validate the result calculation by simulating the circuit with multisim. We learn the distinction between three types of a second-order circuit by examining the output waveform. The critically damped situation will provide the capacitor to the least time to attain its final value. For question 2, we learn how to determine the current and voltage of circuit component utilizing variable methods such as mesh analysis and the superposition theorem. Finally, we use Proteus to prove the calculation result. In simulation, we may determine the phase difference between current and voltage by comparing to the waveform with BS as the reference. Thank you.